Hey everyone, and welcome to this explainer from the Foundry by Forge College. I'm your host. So in our last lesson, we walked through measuring proof of history performance metrics, looking at things like throughput and latency. But that brings us to a rather large, multi-million-dollar question. How do we actually know those metrics are real? Like, how do we know they aren't just completely made up by a validator who's had way too much coffee? Well, today we're putting on our inspector hats. We're going to see exactly how the historical data generated by Solana's proof of history is mathematically proven to be accurate. Ready? Let's dive right in. Think of yourself for a second as a time detective. In the real physical world, if someone claims an event happened at, say, exactly noon, what do? You look for witnesses, right? Or you check the timestamps on security cameras. But we're in a decentralized network here. There's no security footage to rewind. Nodes might be entirely out of sync, or the network itself might just glitch out. You can't just trust a claim. You have to actually verify the engineering blueprints of Solana's clock mechanism to ensure nobody has tampered with the data. We need hard, undeniable proof that a transaction occurred exactly when it was reported, nestled perfectly between the event that happened before it and the event that happened after it. Which brings us to Section 1, the fabric of Solana time. Let's unroll those pattern diagrams and take a look at how this works. Okay, so the core engine of proof of history is what's called a deterministic hash chain. Basically, imagine a perfectly chronological receipt. Every single new hash value that gets generated is strictly and securely computed directly from the hash that came right before it. If you try to go back and change even a single microscopic byte in a past event, boom, every single hash that follows it completely breaks. It's an absolutely tamper-proof chain. Any event anchored in the sequence is provably positioned in time relative to its predecessor. You literally cannot fake the past, because the present math just wouldn't add up. Now, to actually audit this engine, we look at four main components. First, we've got ticks. These are pure time markers, basically the heartbeat of the network, and we check them for unbroken hash continuity. Then, we have entries. These bundle that hash with the actual transaction data. And for these, we verify the hash matches our math and that the payload is completely intact. Next up are slots. Think of slots simply as containers for these entries assigned to a specific network leader. We just make sure they line up perfectly with the leader's boundaries. And finally, signatures. These are the official validator endorsements of the ledger state, which we have to check against the root hash. The whole shebang has to match perfectly. All right, moving on to Section 2, auditing the historical record. Now that we know the parts, let's grab our magnifying glasses. Okay, imagine this. A massive audit report lands on your desk. It claims that exactly 50,000 transactions were processed between two specific hash positions. Let's just call them hash A and hash B. 50,000. That is a massive number. Do we just take their word for it? Obviously not. We're time detectives. Remember, we're not gullible tourists. So to verify this claim, you wouldn't just sit there and count transactions one by one manually. You'd run a strict three-step audit to mathematically reconstruct the timeline and ensure nobody is playing tricks. Step 1, you recompute the chain deterministically. You literally take hash A and run the sequence yourself to see if you naturally land on hash B. Step 2, you check for any missing entries or weird gaps in the sequence indices. And step 3, you verify the validator signatures on those slot boundaries, just to ensure the network leaders actually signed off on this exact data. But wait, what happens if your hashes don't match? Well, you've caught a divergence. Now, don't panic just yet. It's not necessarily a supervillain hacking the mainframe. What could actually be going wrong here? Sure, it could be a malicious cryptographic tampering attack, but honestly, it could also just be a totally benign network hiccup. You might be dealing with partitioned nodes that temporarily dropped connection, or maybe you're looking at pruned ledger segments, or even experiencing basic data retrieval failures. Catching the error is step 1. Diagnosing whether it's an actual attack or just a glitch, that's step 2. Let's keep digging. Section 3, under the hood, code check. Let's look at the actual Rust code logic. So at its very core, an entry structure safely links three really critical pieces of data: the past hash, the current transaction payload, and the new resulting hash. It is elegantly simple, but honestly, it's mathematically profound. You take the previous hash, inject the new data, and out pops the current hash. It creates this unbreakable link between the past and the future. And as you advance through your Web3 learning journey, you are going to see this verification logic everywhere. The algorithm is relentless. You fetch the stored entry data. You independently compute the expected hash using the previous hash and the payload. Then, you rigidly compare your expected result to the stored hash on record. And finally, you ensure that the previous entry perfectly links to the current one. You're constantly checking the links in the chain for unbroken continuity. If everything matches, Your internal consistency is totally flawless. Now, there is a very important distinction we need to make here. Recomputation guarantees internal consistency, but you still need validator signatures for external network consensus. Basically, just because the math works out perfectly on your own laptop doesn't mean the rest of the decentralized world agrees with it. You've proven the chain is structurally sound locally, for sure, but you absolutely still need to cross-check those validator signatures to ensure the wider network officially accepts this chain as the absolute truth. Which leads us to Section 4, relative versus absolute time. Let's break down these two very different ways to track time. Proof of history natively gives you ironclad relative ordering. Because of that hash chain we talked about, we know for a fact that event A happened before event B. And that is absolutely perfect for measuring throughput, like counting how many events fit into a causal sequence window. But mapping this to absolute timing, meaning knowing exactly what millisecond on a wall clock the transaction actually occurred, that requires external clock anchors. If you want to measure fine-grained sub-millisecond latency, you can't just rely on the internal hash sequence. You actually have to correlate those proof of history positions with an external, real-world clock observation. So, wrapping all this up, how does this internal ledger integrity impact real-world transaction speeds? Well, knowing that proof of history provides this flawless structural foundation without needing nodes to constantly pause and check external clocks sets us up perfectly for our next lesson, which is all about quantifying transaction speed. That's all for today's explainer. Make sure to head over to forge.college to continue your Web3 learning journey and explore more amazing resources. But before you go, ponder this for a second. If a network can flawlessly prove the passage of time entirely through math without ever looking at a real-world clock, what other physical realities could we soon replace with code? Think about it. Thanks for joining me, Time Detectives, and I'll catch you in the next one.